All right, this is a presentation on modeling and machining an Archtop guitar bridge. My name's Sam Krimmel, and this project was completed in the summer of 2022. So first off, just a background of what we're going to go over in this presentation, starting with some background on Ken Parker's Archtop guitars. They're really amazing pieces of work. Go over some of the reasons he builds them the way he does. Then we'll cover some of the previous work done on this project. We'll go over the modeling process in Fusion 360, the Akuma OSP U10M control, which is the control for the machine that Ken Parker has at his shop, which is where this bridge was machined. And finally, the steps to machine a complete bridge. So first off, Ken Parker Archtops. Ken began his work on Archtop guitars in 1976 when he built his first Archtop. And then after that, along with his associate Larry Fishman, he founded Parker Guitars in 1991 and made a bunch of amazing electric guitars, super light and ergonomic with a really futuristic design for the time. After US Music bought Parker Guitars, Ken then returned to making his acoustic Archtops. And his goal for all of his instruments is to make them the quote, most sensitive, responsive, and versatile instruments he can. So some information about the bridge on Ken Parker's Archtop guitars. It's all handcrafted right now. The way this process is done is a blank made of ebony, usually ebony, is loaded onto a Bridgeport manual mill, and the part is roughed in linear passes and then cut on a bandsaw and sanded with a spindle sander before Ken has to begin the arduous work of manually carving and chiseling out the inside of this bridge. That said, the bridge is extremely lightweight. It's hollow on the inside. The reason for this is that Ken wants them to be very efficient transducers for transporting the energy of the strings, the kinetic energy of the strings, to the body of the guitar and making the guitar really resonate. The bridge design is also it features a bunch of different angles, but most importantly, the whole bridge is twisted 2 degrees. It's square on the bottom, but as it goes up to the top where the strings are, it twists 2 degrees to account for the intonation differences needed for the different size strings. So some previous work done on this project. In the summer of 2021, a bridge mesh was imported from SolidWorks from the project done in 2018. And that was converted into a boundary representation. And then some surfaces were derived from that. Ken didn't seem to recognize the bridge that was modeled this way, and it didn't seem to have some of the features that he was looking for in a bridge. So in fall of 2021, there were some major revisions made by me on the bridge model itself. Instead of working from a bridge mesh from a previous project, I decided to design a model from the ground up. So I reached out to them and got dimensions of the bridge and modeled that in Fusion 360. Then I went ahead and 3D printed a prototype of sorts and mailed it off to their shop. And Ken confirmed that was the model that he was looking for. It had all the right features, all the right curves. So that was a great success. And then in the spring of 2022, I went about machining this bridge out of aluminum in Washburn Shops. And you can see here the result of that. Used a different process than was used for wood, but it was a really good experience. Getting some experience on the machine with word finding, touching off tools, squaring up stock, stuff like that. So for the model itself in Fusion 360, it's a parametric model, which means that dimensions can be changed on the fly, essentially, which is great for Ken and his work because he's always experimenting with different designs. The bridge bottom, the part that comes into contact with the body of the guitar, is imported from a digitized version of a bridge that was already fit to a guitar. Therefore, any bridges machined to this model should fit, roughly fit a guitar body right off the bat, which is great. Additionally, the model here accurately matches all the crucial dimensions, the thicknesses, length, height, width, all those things. So in order to start the process of machining this bridge at Ken Parker's shop, we had to work around some issues with the Akuma OSP U10M control, which is the control for the machine they have there. It's a great machine, but it's relatively old. And so there were some issues we had to sort out there. First off, there's the post processor problems. Essentially, by posting a toolpath straight out of Fusion using the Akuma post processor, it wasn't exactly the program that it output was not able to be loaded onto the machine and didn't run in the way that we wanted. So I went ahead and edited the post processor from Fusion in Visual Studio Code and added in the necessary G codes and some tool change logic that was required. And so all this essentially put together a custom post processor that Ken and his associate Cameron can use in their shop to post any tool paths, and it should work with the Akuma control. Since the control is pretty old, we needed to work around some file size considerations as well. It has a maximum storage of 62 kilobytes, which is less than a floppy disk. So that was a challenge. To solve that, we had to adjust a lot of smoothing options in the toolpaths, which is it's an option in Fusion 360 to essentially break up curves into more sections, more linear sections, to reduce the file size. So that was set at about 5 thousandths for each file, and that seemed to work pretty well. Additionally, we changed some post options. Simple things like separating words with a space or using sequence numbers we had to disable to get the file size as low as we needed. So for the toolpaths in Fusion 360, it was a really interesting process to go through. There's a constant back and forth process between adjusting the model, writing toolpaths, and then testing them on blanks, and kind of just running through that process and discovering which toolpaths worked and which didn't. Additionally, we needed to think about the fixturing considerations. So every time you generate a toolpath, you need to know where the stock is and how long the tool is. So that had to be taken into consideration with every toolpath that was generated. And then additionally, we had to choose the tools to run through the material. So we had to think of things like the diameter, the rigidity of the tools, and how they would perform in wood. And additionally, the toolpath types as well were really important. We found that scallop worked really well for some of these toolpaths, as well as parallel and trace and project. So that was all stuff that we had to work through. So when it comes to actually machining the bridge, the first, I guess the first step is fixturing the bridge. putting it in the vise in the machine. So there are two different orientations that we needed to get the bridge in. Well, three actually. The first orientation is to machine the pocket, and that's a relatively simple one. We can put the bridge on parallels, put it up against a sideways stock or a stock for the x-axis, and then find the part, touch off the tools, and we're good to go. But then the next challenge was after we machine the pocket, how do we flip the bridge on its side to hold it, because you'd have to hold it between a flat surface and a curved surface, which wouldn't hold it very rigidly. So first we tried this plug idea, shown right here, and this didn't work too well. It was able to hold the bridge in place, but it didn't really support all of the material. So the bridge chattered a lot and vibrated, which resulted in a pretty poor surface finish. And then next we designed this custom soft jaw here, which matches the bottom surface of the bridge. And that way we can clamp it reliably every time, and it really holds all of the material. We put some sandpaper on that as well to add some extra grip. So the next step would be, finding the work and touching off the tools. The way we have it set up in this program, the work can be found once at the beginning of machining a bridge and does not need to be found again. So we reference the back jaw of the vise for the Y offset, reference the middle of the stock for the X offset, which that dimension stays the same as we have that sideways stop pictured right here for the X-axis. And then we just touch the tools off of the top of the parallels. And that only needs to be done once, and then you can run all the operations on all the blanks as long as they're roughed to about the same size. And then the next step, of course, is running the NC code. So the NC code can be posted through the custom post processor that we developed, and then loaded onto a floppy drive. And that needs to be put in the machine, and each program is sequentially loaded to machine the bridge. So next here we got some videos of each of the operations. This first one is just it's called a project toolpath. It follows the outer curves of the bottom of the bridge to rough out some of the material and prevent blowout on the future toolpaths. So it's taking a small amount of material at a time. Just allows it to maintain a good surface finish and not blow out any chunks, any grains. And the next one here is the scallop toolpath. So this comes in and slowly works its way into the center of the part in a similar way to the project toolpath, but it works all the way in, removing all the material and creating that fitted bottom surface that matches the top of the body. It's important to note the direction here. The tool is always going clockwise around the part, which means that it's climbing through the material. In this case, that allows it to not rip up any wood fibers. All right, the next one here is roughing of the pocket. We use a large diameter ball mill just to get a large amount of the material out of the pocket before going in with a smaller diameter tool. This just generally saves time and is good to do to prevent, islands that might flake out and rip some of the material up. You get the idea, goes back and forth, clears most of the material. And then next is the actual pocket finishing. So this tool is really important. It's a tapered ball mill, so it can maintain rigidity while also having a very narrow ball. And again, this is climbing around the outside. and it works its way down to finish the pocket. Here's a video of it going a little deeper. It's doing very small steps here because we want a really nice surface finish within the pocket. All right, next we flip the bridge on its side and we rough out a lot of the material. This is done once on each side first, leaving about, I think 70 thousandths of material on each side. And this allows the wood to kind of settle into place. If you were to remove a bunch of material from one side, the wood could kind of bow up. It's a special consideration with wood. Doesn't really happen with many other materials. So that's done on both sides. A bulk of the material is removed. The bridge can settle in place. And then we go back to each side and we finish the surface there with smaller step over passes with a 5/8 ball mill. That's shown here. And one toolpath that isn't shown in these videos is the toolpath. You can see here there's some grooves cut into the side of the bridge. That's just done with a small down cutting mill or end mill. And we'll go over why that is good in a bit. But to conclude here, some advantages of this process. The machining process is relatively simple and it's replicable. It only requires work and tool finding once. So you can find the work, touch off the tools, and then run, 10 or 20 bridge blanks all in a row, and you don't have to go back and find the work again. And that's due to the way we're holding it and the way we've chosen to remove the material. Additionally, the final bridge blank is grooved. See those vertical grooves that I was talking about earlier? And that allows for an accurate bandsaw cut later to remove this bulk material here. It gives you a line to follow, but it also allows the bandsaw to go through without breaking critical edges on the bridge. So this edge here, you really don't want to blow out with a bandsaw. So that material is already removed, which is great. We were able to obtain a really high quality surface finish on this part. That's due to the use of relatively small step overs, a really dense material like ebony, and large diameter tools. And also the feeds and speeds that we fine-tuned through the whole process. So it only requires minimal sanding and finishing once the bridge is out of the machine. The blank is machined slightly oversized as well. It's a little long and a little tall, so that Ken can do his adjustments by hand. And the process removes about 2 weeks of handwork. And one bridge machining from start to finish takes about an hour, which is a huge improvement in efficiency. And the bridge bottom, as mentioned before, is already roughly fit to the guitar body, removing another big chunk of manual work. All right, that's it. I just want to give a special thank you to my advisor, Professor Manzo. He's been extremely helpful through this project, supporting me the whole way. I want to thank Ken Parker and Cameron Willard. They're the amazing folks at Ken Parker Archtops, and they were extremely generous in allowing me to come out to their shop and work on their machine. Not a cheap machine, I might add. And I also want to thank James Louisel, who helped me in Washburn Shops at WPI, and was always willing to donate his time to this project and to the success of machining a bridge. All right, thanks for listening.